Okay, here we've got a example question of we've got two different forces acting on an object. So let's see. I'm going to create an object here, and just so it's sort of relative and it's personal to me, we've got our object is going to be a jar of Adam's peanut butter. So we've got a jar of peanut butter, and we've got two forces that are acting on this jar of peanut butter. One of them is acting at an angle of 30 degrees, and it's a force of 100 pounds. So a 30-degree angle, 100 pounds would push that jar of peanut butter this direction. It's a 100-pound force, and it's approximately 30 degrees. And then we have a second force that is acting on this object at 150 degrees. So 150 degrees would be a reference angle of about 30 degrees with the horizontal, but it's 40 pounds, which means I've got to make it less than half as much the magnitude as this other force that's 100 pounds. So here's my, let's make a straighter line than that. Here's my 40-pound force at 150 degrees. So if that force is at 150 degrees, of course my reference angle here is 30 degrees. Now, what does that mean happens to the jar of peanut butter? They've got two forces acting on it, two different directions. Of course, the stronger force is going to have more of an influence. We got two ways that we can do this. Since I've got my two forces that are drawn from the object, I'm going to go ahead and draw a parallelogram. So if I copy that 40-pound force, really, you could think about the jar of peanut butter first being pushed upon from here to there, but then also at the same time it's being pushed from there to there. So ultimately what happens to that jar of peanut butter, and I'll go ahead and redraw that red force too, the 100-pound force. What happens to the jar of peanut butter is it ends up being pushed from here to there, and that's the resultant force. Right? So it looks like that resultant force is in the first quadrant. What would be nice to know is what's the horizontal component and what's the vertical component. So we can figure that out. I'm going to go ahead and label these vectors. I'm going to call this first vector vector A, and I'm going to call the blue vector vector B. So I want to resolve vector A and vector B into their horizontal and vertical components. So we've got formulas to do that. We're basically dealing with triangles, right? And so if I were going to look at vector A is this 100-pound force that takes off at a 30-degree angle. And I want to find its horizontal component and its vertical component. And I know that it's got a force of 100 pounds. So for its horizontal component, okay, always the first number. Horizontal component, that means I'm trying to figure out this part right here, right? I'm trying to figure out the horizontal component. So what trig function uses looks like this angle, the hypotenuse, since I've got a right triangle, and the adjacent side, well, that's cosine. So I know the horizontal component, right? I could say that my cosine of 30 degrees is equal to x over 100, but specifically my horizontal component, x would equal 100 times the cosine of 30 degrees. So 100 times the cosine of 30 degrees. And then my vertical component, well, my vertical component would be the opposite there. So what trig function uses the angle, 30 degrees, opposite side, and the hypotenuse? Of course, that's sine. So by the same logic here, I've got that the sine of 30 degrees is equal to y over 100, or that y is equal to 100 times the sine of 30 degrees. And that would be the vertical component for vector A, 100 times the sine of 30. Okay, so I'll use my calculator here in a sec to simplify those two. Let's do the same thing for vector B. Okay, so for vector B, I'll do this in blue just to stay consistent here. So for vector B, what I wanted to do, so vector B is a vector that comes off at 150 degrees, right? And I still have a right triangle here. Okay, my angle is 150 degrees. So let's figure out the horizontal and vertical components for this. Really works the same exact way, right? My force is 100 pounds. My angle, really is 150 degrees, or my reference angle is 30 degrees, but I can use the 150 because it'll keep track of my positive and negatives. Let's go straight to the formula for this one. So for vector B should be 40 times the cosine of 150 degrees. Now cosine of 150 is going to give you a negative value, which is good, right? Because I am going this direction, right? I'm going in a negative x direction. So 40 times the cosine of 150. And then my vertical component would be 40 times the sine of 150. Okay, so I'm going to go ahead and use my calculator for these values now. 40 times the cosine of 150 times cosine 150 should be a negative value, and it is. I've got negative 34.64. And then sine of 150, that should give me a positive value. And in fact, the reference angle is 30. That's going to be 1/2. 40 times the sine of 150 is equal to 20. So I've got my components for vector B. If I do the same thing for vector A, 100 times the cosine of 30, which gives me 86.60, and 100 times sine of 30, sine of 30 is 1/2, so that gives me 50. So I've got vector A and I've got vector B. Okay, I'm going to highlight those two here for us. So I've got vector A broken down into component form. I've got vector B broken down into component form. But really, I want to know what vector my resultant vector is. And my resultant vector here, okay, is equal to vector A plus vector B. Those are the two forces that are acting on this object. So really, this is really easy. I'm just going to add my two horizontal components, add my two vertical components. Okay, so vector R in component form would be negative, if I do vector A first, so I've got 86.60 plus vector B, so minus 34.64. And then for my vertical component, I've got 50 plus 20. Okay, which means that component form for the resultant vector would be, let's see, 86.6 minus 34.64 is 51.96, and 50 plus 20 is obviously 70. Okay, so we've got our resultant vector in component form. Last thing here to do is to figure out the direction and the magnitude of that resultant force. So to figure out the magnitude, it's just Pythagorean theorem. Magnitude of vector R is equal to the square root of 51.96 squared plus 70 squared. Okay, so the magnitude then, let's go ahead and calculate that. 51.96 squared plus 70 squared. And take the square root of that. So our magnitude would be 87.18. Okay, now to find the, and really, so we're just dealing with vector R, right? And we found the magnitude of it because we knew the horizontal component being 51.96 and vertical component being 70. We used the Pythagorean theorem to find the magnitude is 87.18. So now we've got to find this angle. So what angle would use the opposite, 70 over the adjacent side? Well, opposite adjacent, that's tangent. So we know that the tangent of our angle, theta, is equal to 70. That's our y value, our vertical component, divided by 51.96. So theta is equal to the inverse tan of 70 over 51.96. So now I've got to use our calculator for that. Second, tan, which is tan negative 1. Oh, so tan, inverse tan, 70 divided by 51.96, and we get 53.41 degrees. 53.41 degrees. So we've got the direction, force is acting on an angle of 53.41 degrees, and we've got the magnitude. Okay, magnitude of 87.18 pounds. Okay.